Thank you for inviting me to speak at ISMB conference. My name is Sara Taheri and I'm a PhD student in computer science at Northeastern University. Today I'm going to present my research on how do calculus enables estimation of causal effects in partially observed biomolecular pathways. This research is joint work with a number of collaborators at Northeastern University, Harvard Medical School, Pacific Northwest National Laboratories, Next Generation Analytics, and Microsoft Research. Here is the outline of my presentation. First, we cover the motivation of this research and the challenges that it faced and state our contribution. Then we go over the background, methods, results, and the discussion section. Given a knowledge-based graph that represents a biomolecular pathway, many causal queries are of interest, such as when we perturb protein X, what is the effect on its descendant Y? What is the impact of receiving drug A on a specific patient? Estimating causal queries require experimental measurements on the pathway components. However, in practice, many pathway components are left as latent. This is the result of at least two general ubiquitous scenarios. The first occurs when the components of a biomolecular pathway are not fully known. For example, there may be empirical evidence for the regulation of an enzyme, but the identity of the molecule or protein that regulates the enzyme may be unknown. The second occurs when, due to limitations of the measurement techniques, some pathway components are unobserved. For example, antibodies for a protein may not be available. Alternatively, while RNA abundances may be characterized, levels of the corresponding protein or the state of its post-translational modifications may be unknown. Latent variable models are well suited for such estimation in presence of latent variables. However, LVM-based estimation of causal queries can be inaccurate when parameters of the latent variables are not uniquely identified or when the number of latent variables is misspecified, as it is specified in this graphical example. Our contribution is as follows. We prove that LVM-based estimators of causal queries are accurate if the queries are identifiable according to Perel's do calculus. We describe an algorithm for estimation of identifiable causal queries, and we illustrate the practical utility of our approach in 4 synthetic and 2 experimental case studies, where structures of biomolecular pathways challenge the existing methods for causal query estimation. Now, before moving on to the methods, I will give a short overview of some of the necessary background information. An LVM is a probability distribution over observed and unobserved variables. When building an LVM, imagine what kind of hidden quantities might be used to describe the type of dataset. For example, if we have two proteins X and Y, we may think that there exists a latent enhancer that is a common cause of both X and Y. Next, we encode that relationship in a joint probability distribution of observed and latent variables and the parameters of the model. For example, based on the data, we may think that the data follows a linear Gaussian structure. Hence, we encode that into our model. Given observed data on X and Y, we use an inference algorithm to learn a posterior distribution over the parameters of the model. Further, given the model posterior, generate samples for each variable in the model. For example, now that we have a posterior over the parameters theta, we draw a sample for each parameter. Then we draw a data point for u, and then we draw a data point for x based on what we drew for u in the previous step, and then finally we draw a data point for y given the data point that we drew for u and x in the previous steps. An acyclic directed mix graph, or an ADMG, is a way of representing existence of latent variables in a graphical structure. Both networks G1 and G2 have the same number of observed variables, but different number of latent variables. Both networks can be represented with the same ADMG, where the existence of at least one latent variable that is a common cause of x1 and x2 is shown with a bidirected edge. Having a causal query, its identifiability can be decided systematically using an algebraic procedure known as do calculus. In this research, we work with two types of queries: a query in the form of a probability distribution and a query in the form of expectation value. Notice the notation do x equal to x prime. This is different than a conditional probability notation that we are all familiar with. That is the probability of y given an observation on x, while p of y given do x equal to x prime is the probability of y given an intervention in x. This means that the value of x is fixed to a constant value x prime. Hence, x is no longer affected by its upstream nodes. For example, the causal query in the top graph is not identifiable. This is because of the existence of latent variable u. In the bottom graph, the query is identifiable because now we can first estimate the effect of x on z and then the effect of z on y. Figuring out if a query is identifiable in a graph is not easy. Luckily, there exist several implementations that take the graph and the query as input and determine whether the query is identifiable according to do calculus. Now we are ready to talk about the method section. This section focuses on the LVM-based estimation of causal queries and show that these estimates are accurate if the queries are identifiable according to do calculus. I will start with a motivating example. Assume this causal graph. The query of interest is not identifiable according to do calculus. Assume that given observed data x and y, we use an inference algorithm to learn a posterior distribution over parameters of the model. Then draw a sample for each parameter from its posterior distribution. Next, sample a data point for the latent variable u, fix the value of x to its intervened value x prime, and finally draw a data point for y. For each sample theta, repeat steps 2 to 4 many times. Hence, for each sample theta, you can generate a density plot, which are the green curves in this plot. We can see that the estimated curves do not represent the true curve well. Now imagine a situation where there is a mediator z between x and y. In this case, the queries of interest are identifiable. If we repeat the same sampling procedure, this time the green curves will represent the true distribution well. Hence, with this simple example, we showed that the LVM-based estimators of causal queries are accurate if the queries are identifiable according to do calculus. The following theorem proves the empirical result in the previous slide for a general case. It proves that in general, for any LVM topology, any set of parametric distributions, and any identifiable causal query, the generative sampling procedure accurately estimates causal queries in an LVM that correctly reflects the true underlying causal structure. But what if we are not sure about the structure of latent variable? What happens if we misspecify the true number of latent variables? The answer to this question is that the queries can still be accurately estimated even when the true number of latent variables is misspecified, as long as the misspecified graph projects onto the same ADMG as the correctly specified graph. For example, G1, if G1 is the correctly specified graph and G2 is the misspecified graph, since both project into the same ADMG, we are still able to recover an accurate estimate for the queries of interest. Due to time limitation, I provided results for some of the case studies in our paper. However, in the paper, we illustrate the practical utility of our approach in 4 synthetic and 2 experimental case studies, where structures of biomolecular pathways challenge the existing methods for causal query estimation. We refer you to read our paper for a full description for rest of the case studies. This is a synthetic case study called the COVID model. In the last 2 years, COVID-19 has been a major concern for many. Currently, there are many COVID-related research available. This provided my collaborator Jeremy Zucker and his team in the COVID-19 disease map with a trove of biochemical details about the novel coronavirus and how our immune system responds to it. Taken together, those details can be represented as a causal knowledge graph as in this figure. This system models activation of cytokine release syndrome, known to cause tissue damage in severely ill SARS-CoV-2 patients. The simultaneous activation of NF-kappa B and IL-6 STAT3 activates IL-6 AMP, which in turn activates cytokine storm. The network was extracted from COVID-19 open research dataset. The queries of interest examine the ability of 2 different drugs to prevent cytokine storm. Tocilizumab or TOSI is an immunosuppressive drug that targets SIL6R alpha and blocks the IL-6 signal transduction pathway. So the first query of interest is the effect of SIL6R alpha on cytokine storm by setting low values to SIL6R alpha. The second drug of interest is gefitinib or Gefi, which blocks EGFR. The second query examines the effect of Gefi on cytokine storm. The challenges of this case study was that the cause is continuous. Estimating the causal queries in this situation where the cause is continuous is very challenging in non-LVM approaches. Also, the data generation process involves a mixture of distribution for this case study. This case study showcases the case where you train a single latent variable model and you are able to answer multiple queries. Imagine answering thousands of queries by a single training of the latent variable model. The results of estimating the causal queries over 20 dataset shows that the LVM with correct topology, that is represented with orange box, and the LVM with misspecified number of latent variables, that is represented with blue box, both converge to the true value of causal query as the number of data points used to train the model increases, and the difference between the LVM with correct topology and the LVM with misspecified number of latent variable will decrease as the number of data points increases. The second case studies are the experimental case studies. The data for these case studies are from the paper by Sastry, which was published in Nature Communications in 2019. The data contained 278 RNA-seq normalized expression profiles of E. coli across 154 unique experimental conditions. Interventional data corresponded to the query of interest was available, hence we had a measure of the ground truth. We can see that despite real-life experimental artifacts such as dynamic range compression and measurement errors that affected the observational data, and despite the approximate nature of modeling assumptions, the estimated distributions covered the values observed from the experimental interventional data. A common criticism of latent variable models is the requirement of parametric distributional assumptions. We showed that even though the LVMs imperfectly approximated the unknown data generating distributions, the estimates were accurate. An LVM trains on observational data once, then can estimate multiple causal queries corresponding to multiple mutilated versions of the original DAG. After training, the estimation of causal query is instantaneous. This indicates that with enough experimental replicates and computational resources, the proposed approach can be scaled to larger networks. The proposed approach expanded the current use of LVMs for estimating causal queries. The estimation is robust to latent variable misspecification and to parametric approximations of complex processes of data generation. As all these situations are very common, the proposed approach expands the feasibility and scope of causal inference in biomolecular pathways. And that brings us to the end. Thank you for your attention.